Swayam Prabha. Digital India. Educated India.
Good afternoon, students. Welcome to lecture 6. In lecture 6, we will be covering the product life cycle and we will look at concepts in CAD and reverse engineering. So, we will move on from sketches into CAD concepts and we will also look at reverse engineering. So, at the end of today's lecture, you will be able to understand and take a whole life cycle approach to product development. You will understand the basic principles of computer design. You will be able to understand and articulate key concepts in reverse engineering, and you will learn how to apply reverse engineering concepts and life cycle management approaches to new product development for complex products. Okay, so, let us think about the product life cycle. What is the life cycle of a product? So, it is said that a cat has 9 lives, but this is true of products too. So, from introduction to consumers to no longer available in the market. So, eventually many products they just go out of circulation. So, it is a matter of debate what are the exact number of stages in the life cycle of a product. So, the concept of the product life cycle was first proposed by this gentleman Raymond Vernon, and it is essentially that no product lasts forever. So, what are the life cycle stages of a product then? So, we talked about development in the previous lectures. So, you have sort of started to understand how to develop a new product. We talked about new product development, how to develop a new product. But after you have developed it, you need to then introduce it into the market. You need to introduce it into the market, then you want to see it grow, capture a certain market share. And then the products typically go through a phase of maturity, where the sales sort of become even and do not grow with time, they saturate, and then the sales decline. So, the product is less and less used and new products are taking hold in the market. So, do these stages make sense to everyone? Development, introduction, growth, maturity and then decline. So, let us talk about these phases. In the development phase, the product idea is living with the manufacturer. Okay, the manufacturer of the product, he has got the product idea. So, he researches the idea, he tests and prototypes it. Okay. So, that is where you are developing the product. So, an example of the development phase is for Tide Pods. Does anyone know what Tide Pods are? So, it is a detergent and it comes as a as like a little sachet, yeah, and you just throw it inside in the drum of your washing machine, and when it goes through the washing cycles, then it releases those chemicals which clean your clothes. Okay. Again, developed by Tide, everyone knows Tide. So, these are some examples of Tide Pods. So, images. So, it took 8 years to develop, they are probably not that popular in India, and 450 plus sketches. Okay. 6,000 consumers were researched and they developed various formulas during the process. Okay. So, see how much work goes into developing a product which you might think is quite simple. Okay. So, now we can talk about the next phase in the product life cycle, which is growth. In the growth phase, the consumers are aware of your product, they know that it exists in the market. Okay. So, there is a real growing demand. So, demand for the product is increasing, and in this phase also other competitors are popping up who are offering the same features. Okay. So, now today of course, those button phones are completely almost out of fashion. right? So, almost everyone, Sony, Motorola, Samsung, Nokia, everyone makes these sorts of phones which are full screen, full touch screen displays. Okay. And then there are new feature requests. So, the customers, when they start using it, they also come up with their own ideas. I want this, I want that from the product. So, you bring those in, you respond to queries from the customers in the growth phase. So, they will face some issues when they are using the product. So, Google launched its first Android smartphone in 2008. Samsung introduced the Galaxy tablet to compete with the iPad. So, these are all the competitors that are cropping up. Okay. By 2011, smartphones had outsold PCs. Okay. So, that shows the growth in the smartphone market that took place between the first iPhone launch and 2011. So, Q4 of 2010, 100 million smartphones were sold compared to 93 million PCs. And then once you have gone through growth, then the product matures. So, there is the end of the rapid growth. Your item is a familiar product, lots of people around you have it. The target consumers own it, whoever the companies had targeted, they own it. The sales are leveling off. Okay, so, there is no more quarter on quarter increase in the sales. The most profitable stage is maturity, and it is also the most innovative, because then you are starting to think about new products. So, you make updates to your product in this phase. The prices may drop in this phase to stay competitive, and then you want to be differentiating your product and positioning your brand as well in the maturity stage. Then the product goes through a decline. So, BlackBerry is almost out of fashion. So, they have gone through a clear decline. Some products decline because they have aged out of the market from a technological standpoint. So, instead of these push buttons, you have the touch screens. So, others, they become obsolete because they have lost their market share or failed to adapt. So, for instance, very few people use Yahoo today. Any of you uses Yahoo? Yahoo had a very narrow mindset, which was we are going to grab content, put it in front of our users and call it a day. Okay. So, they were one of the very early search engines. There was one called Alta Vista. Anyone recollects? Yeah, no. So, there were these early search engines which nobody uses now. Okay. Google has a much better search algorithm. So, they own the world, but they were not looking to the sky. Okay. So, that is, these are the words from the former creative director for Yahoo, Tom Parker. Okay. So, you do not want to be stopping with the launch of your product, you want to be continuously innovating. Okay. So, what is the product management's role at every phase of the product life cycle? So, you will have people in a team who are subject experts. There are people who will be growth hackers, they help you grow. There will be retention strategists and there will be solution seekers. Okay. So, in the introduction phase, the subject expert is important. His or her goal is to get the product to be getting to ensure that there is a fit between the product and the market. The growth hacker comes in the growth phase, and his or her goal is to expand the reach, the scale and stay competitive. So, expand the reach of the product. So, maybe it is selling in one region of the world, then take it to another continent, another country, another region of the same country. So, that is what the growth hacker does. The retention strategist tries to retain the product in the market, sustain the market share in the maturity phase, and the solution seeker thinks, well, what should we do next? So, determine the best outcome for in the decline phase of the product, whether we should go for a similar product with improved features or create a completely new product. So, subject expert, his focus is to adapt rapidly to the new insights from the customers in the market. So, early user feedback, so that you can really make it fit for market. The growth hacker wants to support more users while optimizing to accelerate the growth. Okay. Support more and more users, expand the reach. The retention strategies evolves the value of the product and the value proposition of the product. So, what other value can this product deliver? Can it be used in other applications? Can it have some other usage? So, that can give you some increased sales in the mature phase. So, the retention strategy tries to bring in customer satisfaction and delight while battling the churn that's occurring and the other competitors coming into play. And the solution seeker is thinking strategically about pivoting, resurrecting the current offering or phasing out. So, he has to make these choices. Okay. Should we keep it? Should we make another product which is similar? Should we bring in new products? So, typically your sales will vary something like this. Until your product is developed, of course, there are no sales, and then once you introduce, the sales start increasing, where you are growing a customer base, you are building a brand, and you are taking care of your pricing and distribution. And then the growth phase, you start making your profits, there is growing demand for the product and the first competitors come around. Then in the maturity phase, you can see the sales are tapering off. Okay, there is not much increase between here and here, whereas here you can see how much of an increase is there, yeah, in the y axis. And then in the mature phase, the sales peak, the growth stabilizes, the market satures, and you need to innovate. And in decline phase, of course, your sales start dropping and you may reinvent or ramp down the product. And the task for you will be, just think about these questions. Okay. So, what stage of the product life cycle is this product in? What are the key engineered features in this product? How long do you think will this product last in the market? What improvements can you add to this product? What ideas for future products can you imagine based on this idea? And how do you build this product based on what you saw in this video? So, let us begin with reverse engineering. What is reverse engineering? Well, reverse engineering is the process of duplicating an existing component, sub-assembly or product without the aid of drawings, documentation or computer model. So, let us say you have a chair, this chair here, and you are asked to make a copy of it. Okay. To make the copy of the chair, you are not provided with any kind of drawing, you are not provided with any kind of documentation or computer model, you are just given the actual product. Okay. So, how do you go from this actual product to making your own product, which is a copy of that? Okay. So, that is reverse engineering. So, imagine there is a tractor that is developed by a certain company, and then you want to make a tractor which is the exact copy of that. Okay. But you are not, because it belongs to another company. So, you cannot use their drawings, documentation or computer model. And let us say you are given a task of making a copy of it, then what you do is reverse engineer it. Okay. So, you do all of the engineering based on the product itself, the existing product. So, reverse engineering is the process of analyzing a product to identify the components. What are the parts that make up the product? Okay. What are the components and how are they related to each other? What are the relationships between the components? It is also about creating representations of the product in another form. So, can you create another representation of the same product? So, it may be a 3D model of an existing physical product. It may be some drawings of this existing physical product. Okay. So, those are other representations of the product. And finally, the goal is to create the physical representation of that product. So, there is no point in creating all these 3D CAD models and drawings, etc., if you cannot use them to create the physical representation of that product. So, reverse engineering is quite common, and there are lots of fields that use reverse engineering. These include software engineering, entertainment, automotive, consumer products, microchips, chemicals, electronics and mechanical designing. So, you can imagine any field today, there is reverse engineering going on in all of these fields: software, entertainment, automotive, consumer products, microchips. So, all of these fields are using reverse engineering, and the techniques for reverse engineering vary from field to field. So, some examples of reverse engineering: when new design comes to market, competing manufacturers may buy one of these designs and disassemble it to learn how it was built and how it works. So, let us say a new smartphone comes out. So, competing companies, let us say Apple has launched a new smartphone, other companies like Sony, Samsung, Nokia, etc., they can buy that iPhone and disassemble it and then learn how it was built and how it works. So, take the existing product which has come out and learn how it was built and how it works. So, a specific example is that of a chemical engineering company that uses reverse engineering to defeat a patent on a competitor's manufacturing process. So, maybe there is a competitor who has filed a patent application on a manufacturing process. Now, the competitor of this company may come around and say, okay, I was able to reverse engineering it, and so there is no novelty in that patent. So, they may be able to defeat the novelty claim that the competitor has put out. So, every year companies file lots of patent applications, and these patents will restrict other people from using that process or product, right. So, there is a patent war going on all the time, and in this patent war reverse engineering plays a key role. Again, in software engineering, good source code is often a variation of other good source code. So, you might take source code that exists and then use a patchwork approach and create your own code. Just like I showed you examples of the ultrasonic sensor, the smartwatch, etc. There what I did was I created a variation of existing source code. So, you do not have to write your code from scratch, you can take code that exists and then add your own interpretations, own layers to it, so that you come up with code that works for you. Likewise, designers give a shape to their ideas using clay, plaster, wood or foam rubber. This is again an example of reverse engineering. So, using clay, plaster, wood or foam rubber, you can give shape to your ideas. So, and that can then help you create a CAD model which helps you manufacture the actual product. Using clay or plaster, you can cover up, let us say, a car, and that gives you the outer body of the car, which you can then use as a mold to manufacture the same shapes, or you can use it to create a CAD model from which you can manufacture the actual product. So, when is it used? Well, reverse engineering helps you to carry out rapid product development. Okay, so, you develop products quickly, it helps you compress product development time. So, let us say a new smartphone has come out, instead of guessing what is there in that smartphone, if you open it up and you find out all the components, then you can then realize your own product in lesser time. So, an example is that of an injection molding company. They use they typically need short tool and die development times. So, what they normally do is they use reverse engineering to capture a 3D product in digital form, remodel it and export it for rapid prototyping. So, the way that is done is using various methods of dimensional metrology. So, these days there are laser scanners, you can use laser scanners to scan a part, and that creates a point cloud, and from that point cloud you can get a 3D model in digital form. You can use that to remodel and export and create rapidly prototyped parts. So, reverse engineering is quite effective, cost effective when there is high investment or mass production. So, if you can invest in large amount and you carry out mass production, then it is quite cost effective. So, the money that you spend in reverse engineering, you make it up very quickly because you make multiple copies of that same product. Sometimes even if it is not cost effective and if it is quite critical to a certain mission, certain project, then companies may still attempt to reverse engineer parts or the entire product. Okay. So, if it is very crucial to the functioning of your product, then you may carry out reverse engineering. So, let us look at the reverse engineering of products and machines. So, here you can see a ATOS COM laser scanner. So, this is the laser scanner, shines a laser beam and this laser beam falls on parts like this, and based on the reflections a point cloud is generated. So, measuring an object and then reconstructing it as a 3D model is what this laser scanner enables. So, there are many such measuring and scanning technologies now. There are coordinate measuring machines. How many of you are familiar with coordinate measuring machines? Coordinate measuring machines are ones which have touch probes. These touch probes, you can fix a part on a bed, and then these touch probes, they go through the entire part, they touch the part and go through, and as they touch, they get the x, y and z coordinates of the part, okay, and they create a cloud of the points of the part. So, they help measure the coordinates of the part. So, instead of a laser, you have a touch probe that goes through the part in steps, maybe in steps of 5 millimeters or 2 millimeters or 1 millimeter, and they touch the whole part this way, and then they may also go this way, and then the points that you get, you can use that to create a mesh. So, those are coordinate measuring machines. Equally, you may have laser scanners. So, like the one shown in the right. You also have structured light digitizers, and you also have industrial CT scanning devices. So, many different devices are available now to scan parts and create a 3D model of that part. So, this point cloud that you get from scanning the part, it lacks topological information, and it also does not have design intent. So, it is just a set of points in space that you see on the computer screen. It does not tell you how those points are connected, and also it does not tell you what is the intent of the designer that went into creating this part. Now, for the topology, what you can do is you can convert the point cloud to a triangular faced mesh. So, you can take these points and you can join these points to create triangles. So, these triangles will then represent the surface of the part, and this is typically stored as STL files or stereolithographic files. So, the name stereolithographic comes from the process stereolithography, which is a additive manufacturing process or 3D printing process. Okay. So, you get a triangular faced mesh by joining these points in the point cloud and creating triangles, and you can store that as a STL file. So, thought question for everyone: briefly express your opinion on the following uses of reverse engineering: blindly, mindlessly or artlessly copying another's design, blindly, mindlessly or artlessly copying one's own design, hacking, exploiting, and of course, when you are thinking about this, be sure to consider how you would feel if it was your design that was being copied or hacked or exploited. So, maybe you can discuss in groups on the following uses of reverse engineering: copying others' design, copying one's design, hacking and exploiting. What is your opinion on these uses of reverse engineering? Okay, so now let us talk about some historical examples of reverse engineering. Reverse engineering has been quite popular for military and defense applications. So, these are some fighter aircrafts. So, this is a B-29 bomber, this is Tu-4 from the erstwhile USSR, this is a F-22 from the US, this is a Sukhoi Pak-T, X-29, Sukhoi Su-47. Again, all of these fighter aircrafts have been at some point of time been reverse engineered by other countries. So, reverse engineering has been commonly used for military espionage. So, that is a key motivation for reverse engineering. So, an example is that of the German jerry can was reverse engineered by the British and the Americans. The German V2 rocket was reverse engineered by the US and USSR. Again, people have tried to copy the Coca-Cola formula. So, that is an example of industrial espionage. Again, a lot of companies These days they try to indulge in competitive technical intelligence, which is watching all others through their production models. So, all the car companies, you will see they are constantly looking at what car models are coming out from the other companies. They are constantly watching and they are constantly studying. They are immediately going to a market and getting a copy and trying to understand all of the engineering that has gone into that new car model. Again, smartphone manufacturers are also constantly watching their competitors. So, we are in a world where reverse engineering is fairly common and it is required, otherwise it is very difficult to stay competitive in the market, and therefore, one of the key motivations for reverse engineering is competitive technical intelligence. Again, product security analysis is a good motivation. Is your product secure enough? Okay, analyzing that. So, that is usually possible by cloning, for instance, the product. So, clones of the original IBM desktop computers and Intel processors have been used for product security analysis. So, is your product secure enough? To test that, you might need to clone other products. Reverse engineering may be required to improve the shortcomings in documentation. So, replacement of broken or own parts that may not be available in the documentation. So, you may have to use reverse engineering to be able to create those parts. It is particularly useful when the original manufacturer is no longer in business. So, let us say you created a navy ship and at that time there were lots of suppliers and you purchased those components and you built your ship, okay. And that ship may have some engines, it may have some gears, pulleys, shafts, all sorts of parts. So, those parts may maybe 10 years to 20 years down the line, when the ship is still in operation, the manufacturer may no longer be in business. So, you may not be able to get those parts, and in that case you may have to do reverse engineering. So, you can argue that in such a case also copying the design of somebody else is acceptable, because that manufacturer is no longer in business, right. In that case, you can argue that it is ethical, because you have a ship that costs maybe £1,000,000 and you still want to keep it running, and it has only a few parts that need replacement, and that cannot be replaced because the manufacturers are no longer in business. Okay. Reverse engineering is also used for academic or learning purpose. So, to learn about something, you may have to reverse engineer that product or part or code, whatever it is. So, an example is the anti-Behera mechanism. So, do look it up and see how it was used for learning. So, maybe ancient mechanisms, if you come across ancient devices, okay, which are from 400, 500 years ago. So, again for those sorts of devices, you may carry out reverse engineering to understand how the ancients, how the people several hundred years ago, how they use those parts and components. Okay. So, reverse engineering has a lot of value. So, sometimes reverse engineering is used for unlicensed and unauthorized duplicates. So, this is where the ethics comes in. So, you will see in the market there are lookalikes for Rolex watches, there are lookalikes for handbags, all sorts of designer products. So, there are lookalikes, and they even sell these products with the original manufacturer's labels, and those will come much cheaper. So, it is an interesting topic. Yeah. So, reverse engineering is an interesting topic and it is used for all sorts of purposes, good and bad. So, let us look at different types of products, how the designs vary and where you might need reverse engineering. So, televisions, the original design that was from John Logie Baird in the 50s and 60s. So, those used cathode ray tubes. Okay. So, small screen analog black and white cathode ray tubes. So, this was adapted to create larger screens. So, analog color cathode ray tubes, and then it was further adapted to create this developmental design. So, adaptive just adapts the original design. and developmental really brings in a step jump. Okay. So, there is a technology push. So, due to the technology push, your product gets upgraded, you are getting the same functionality, which is to see moving images on screen, and what happens is you use a new technology. So, digital TVs, HD TVs, plasma TVs, LCDs, OLEDs, all of these are technology push products. So, technology has changed, the functionality remains the same, and you can create variants of the original design. So, variants of these would be larger screens or mini screens. So, the technology remains the same, but you just project it to a larger screen or mini screen. So, that becomes a variant design. Do you all understand the difference between original design, adaptive design, developmental design and variant design? So, likewise for telephones, automobiles, airplanes and home energy, you can see how the technology push has changed the original design to the developmental designs, and how the market pull has changed it from an original design to adaptive design. So, when black and white cathode ray tubes came out, people started asking for color cathode ray tubes. So, the adaptive design resulted as a result of the market's needs. So, to create these adaptive designs, the developmental designs and variant designs, again you would have to understand the original design and modify it to create these adaptive designs, or understand what are the limitations in the original design. So, reverse engineering helps you to understand the original design properly, so that you can either adapt it or develop it. So, key step in reverse engineering is tearing down the original product or disassembling it. So, here you can see a gearbox, okay, and this gearbox has been shown with all of its parts separately shown. So, this is known as an exploded view. So, if you use a CAD software tool like SolidWorks, you can, after you created your assembly, your product, you can explode it, and when you explode it, then you can show the parts all separately. Instead of being together, mated together, you separate out them, and then you carry out a dissection and technical analysis. So, what you do is you take the product and you tear it down, you dissect it and then carry out a technical analysis. So, once you have taken it out and you have separated out all of the parts, then you can label them and create and understand what are the parts that go into that gearbox. So, for instance, in this gearbox there is a case seal. So, this is a seal for the case that will be applied somewhere here. There are some gears, there is a suction port, there is a seal here again, there is a drive shaft, there is a mounting flange, there are some pressure ports, some bushings and some idler gears. Okay. So, this is a gearbox which essentially houses this gear, okay, but it has to be housed in this box which requires all of these other components. So, this outer frame here goes in together with the seal and pushes this gear into this chamber, okay, and this chamber and this frame are locked together with the seal and these fasteners. Okay. So, using this fasteners, this is kept in place inside this housing, and that is how you create your gearbox. So, you may be given a gearbox, but you do not know how to make it. So, the way to make it would be to dissect it and find out all the individual components and then label them, and then you know all the parts that make up the gearbox. So, this tear down and assembly gives you experience and knowledge about the part. It also helps you benchmark. Let us say you have your own gearbox, then you can compare this gearbox to your own gearbox and see what are the shortcomings or what are the additional components, or maybe have they used the modular or integral design that you can incorporate into your product. So, what is the tear down process? So, the tear down process involves looking at every part that makes up the product. So, you have to look at every part just like we saw in the previous slide. So, you create this exploded view where parts are laid out to reflect how they went together in the assembled product, and then you want to observe this exploded view. Okay. So, you create your exploded view, then observe it in terms of its shape, its size and its finish. So, 3 key attributes that people typically look at: shape, size, finish. But that is not all, you want to find out also how are they oriented, are the parts, how are they aligned, okay, in which axis. So, shape, size, finish, orientation, these are the things that you want to find out, and then you want to find out how they mate, okay. How do they mate to create the final product, and how are they arranged within the whole product. So, all of these attributes you need to observe them, and then once you have done that, the next thing that you want to be doing is identifying, well, what material was used to make each individual part. Identify the material of construction for each part. So, these may be metal, ceramic, glass, wood, polymer, rubber, composite, etc. So, that is a basic identification, and then further identification could be that you find out what specific alloy it was, what is the chemical formula of this ceramic, okay. What is the texture of this glass, how was it potentially made. If it is wood, is it teak, is it sesame, is it pine wood, what type of wood is it. So, identify the material of construction for each part. Then you want to be identifying the method of construction or fabrication and processing. Okay, so, how was this shape realized? Did we use casting, forming, welding, machining, 3D printing, injection molding? What did we use to make the part? Okay. So, identify the method of construction or fabrication and processing. So, it could be machining, casting, plastic injection molding, forming, welding, all sorts of manufacturing process. So, these are processes you might have learnt in your first year of engineering. Are these familiar to everyone? Yes, raise your hand if you have. Okay. Then you want to be finding out what functionalities they have. So, what you can do is you can disassemble and remove one component or feature of the assembly and see if you can operate the altered product. Okay, remove just one component, see what it does. Okay, can it still do what it was originally doing? If not, analyze the effect of the subtraction, that will tell you what functionality that specific part had. So, deduce the function of the subtracted component and then replace the component and repeat the procedure for each and every component one by one. So, put it back, take another component out and see what effect that has. So, translate the collection of sub functions. So, for each part that you disassemble and remove, you will get a sub function and then you can collect these sub functions and create a function tree. Okay, so, there is a specific, it is not just about okay, there is a product, we just break it down, we know all the parts and we can make our own product. No, you also want to be knowing what is the function of each part in that product, and only when you deduce the function that then you can realize your own product and get it to work. Or maybe after learning about the sub functions, you may come to a conclusion that some of these functions are not needed for your own product, and so you get rid of those parts and you make a more compact or a design that is maybe cheaper or functions better. So, a critical part of reverse engineering is to create these force flow diagrams. Okay. So, let us look at an example. So, this is a paper clip. So, if you look at this paper clip, you can see here how the force flows. Okay. So, you squeeze at these lower arms. Okay. So, then the spring clip opens to these dashed lines, and that is how you can place the paper in between the clips. Okay. So, you can take this simple product and you can annotate it to write out the functions, which is squeeze at lower arms and then spring clip opens to dashed lines, and then you can also label the parts which are rotatable lever arms, and this is the pivot for the lever arms. So, once you have done that, then you can come out with your alternative design. So, you can see some alternative designs of paper clips. This is the owl design from 1908, this is the ideal design from 1902, this is the easy on design from 1920. So, the paper goes somewhere in between here, somewhere in between here. So, this is a common sense design from 1904, this is a Weiss clip still used from 1904. This is also quite common, the gem paper clip from 1892. There is a Philadelphia design from 1867, Rin clip from 1905, There's a Niagara clip from 1897 and Curly clip from 1936. So, see how the designs have changed over the years. At the end of the day, all you are doing is you are just putting paper together, so that they do not separate out and get interchanged. So, we talked about disassembling the product and creating all the parts, and once you have done that, what you can do is you can create this product structure breakdown. I think we talked about product structure and product architecture before as well. So, what we will end up is with this technical system which has n number of sub assemblies, and each sub assembly has a number of components. So, for instance, for a transport airframe, you may have a fuselage, wings, engines, empennage, and the empennage may have components such as left horizontal stabilizer, right horizontal stabilizer, left elevator, right elevator, vertical stabilizers, rudders, etc. So, once you have done your product structure breakdown, the next thing you want to be doing is your functional models, and functional models are typically created by creating these sub functions that add up to give you the overall function. And the function is typically written as a verb. Okay. So, it is showing some action, some verb acting on something to create or to produce, or these sub functions will add up to give you the overall function. And the functions will have as input maybe some energy, some material, or some information. So, inputs could be energy, material, or information, and as you flow through you can deduce the overall function, and the outputs will also be some energy, material, and information. So, each function here is the function of a subsystem of your product. So, let us look at an example. So, this is the Sear bonder model LT160. So, it is used to create a bond between two components. So, as you can see, it is shaped like a gun. So, you press here. So, there is a easy squeeze trigger here. There is also an on off switch because it works on electric power, and once the power comes in, there is a power indicator light which will tell you whether the power is on or not. There is an insulated nozzle cover, and there is a tip, and the glue comes out from here, and this is where you can place your glue sticks, and this is your high temperature full size glue gun. Okay. So, this is where the melting of the glue takes place. So, it uses the power that comes in to melt the glue, and then when you squeeze it, it comes out through this nozzle. So, you can tear it down, and all the individual components will then be evident to you. So, you will know what springs are in there. Okay. So, what is the shape of the trigger assembly? There are two springs, there is a tension spring and there is a compression spring. There is a cord, there are some heating plates, some wires, some screws, etc. So, then you can draw a force flow diagram for it. So, the force flow diagram shows how it works. So, from your hand there is a trigger that goes to an arm of the glue gun, and that trigger then moves the glue stick clamp, and that then moves the glue stick along the shaft of the glue stick clamp, and it goes along a guide. Okay. And then that goes through a rubber guide, and then that is released. Okay. So, likewise you can see where the force is flowing from the hand to the case, and from the hand to the trigger. Okay. And to the trigger to the linkage arm. So, you can see where the force that you are applying to the glue gun, where it flows. So, it goes. So, when you press the trigger, it also goes to a tension spring as well as the linkage arm. So, if there are two parts to which the force flows, then you want to be showing them separately, and then that force goes through to the glue stick clamp. So, you want to be showing all of the parts through which the force flows. So, that is how you get your force flow diagram. Bit complicated, you can take a few products and try making force flow diagrams for yourself, and then you will get the hang of it. So, if we look at the functional model, that is different from the force flow diagram. The force flow diagram is just showing where the force is ending up, okay, and through what all parts in the product the force is going through. But the functional model will tell you how it functions. From the energy that you apply with your hand, that induces a translational force in the glue gun, that is converted to a rotational force, which is then used to secure the glue stick and translate the glue. The electrical energy that you are getting through the plug-in cord, that is getting converted to thermal energy, that is melting the glue, and then it is going through to the guide in the glue gun, and then it is getting placed correctly. So, your hand is used to translate the glue and the electrical energy is used to melt the glue. Okay. So, you can come up with this kind of a functional model, and this is only for a simple glue gun. Imagine what the functional model for an entire tractor or a car or an aeroplane will look like. So, that gets even more complicated, but this is what you need to do to be able to carry out your reverse engineering, create a force flow diagram and create a functional model. So, let us move into computer aided design. So, these are examples of computer aided design tools in action. So, on the top left you can see wireframe model of a car. The top right you can see a housing of some sort. Okay. Bottom left is a robotic arm, and on the bottom right is a torch with some electronics in it. So, using computer aided design we can create these sorts of 3D CAD models of products. So, there is CAD and there is also CAM. So, CAD is the use of computer systems to assist in the creation, modification, analysis or optimization of a design. So, it is about designing the product, okay, using computer to design the product. That is what CAD is. CAM is the use of computer systems to plan, manage and control the operations of a manufacturing plant through direct or indirect computer interface with the plant's resources. So, it is about manufacturing the part, using the computers to manufacture. So, once you have created the 3D model of the part, then you can maybe generate tool paths. These tool paths can be fed to a computer numeric controlled machine, okay, to mill out the part or form the part. So, that is CAM. Using computers to carry out manufacturing, that is CAM. Using computers to carry out design, that is CAD. So, why do we need CAD CAM? So, CAD CAM enables us to increase the productivity of the designer. You can create designs quicker, okay. It takes ages to sketch out your ideas on paper, whereas with CAD you can alter your drawings, your 3D models on the fly, and you can create new designs quickly. So, that improves your productivity. Whereas, if you had 5 or 6 design ideas and you had to lay them out on paper, it would take you several hours of drafting each single drawing. It also helps you improve the quality of the design, because once you have a 3D model, then the annotations are very clearly laid out, okay. All the dimensions are specified. So, anybody who has to manufacture it can readily read your design and convert it into a product. So, the quality improves because the legibility of your drawings improves, and there is a complete sequence from your ideas into a final realized concept, which and in which there is little ambiguity. So, CAD CAM also helps you improve communications. So, once you have a 3D model, then you can communicate it to anybody in your company, or you can communicate with your colleagues, etc. So, you just need to send one file, a digital file. It also helps create a manufacturing database. So, all the products that you have made, you can create a database out of it. You can create and test tool paths and optimize them for CAM, and you can also carry out production scheduling, and you can carry out manufacturing resource planning. So, you can schedule your production based on the 3D CAD models that you have made, because it breaks down into individual parts, and then those individual parts you can also estimate the machining cycle times for them, and based on that you can schedule your production and you can carry out your manufacturing resource planning. So, overall it helps you have effective shop floor control. So, due to CAD CAM, your manufacturing is completely streamlined and you have better control over your shop floor right from your desk. So, CAD is also used to manage design changes, improvements, structure assemblies and manage large designs with complexity. So, CAD is very useful in making design changes. If you had to make simple changes to your drawing, you would have to either erase them and create, which would look ugly, or you would have to create, in the olden days you would have to create a new drawing. So, managing design changes was difficult until CAD came in. So, CAD is very helpful in design change management, making improvements, structuring your assembly. So, creating a hierarchy from product to sub assemblies to parts, and managing large designs which have complexity. So, there are two main approaches to CAD. One is the bottom up and the other is top down. So, you can start with the components to build up a final assembly, or you can take an assembly and break it down into smaller components. Okay. So, you can take an assembly and break it down into smaller components, or start with the components and create the final assembly. So, the first one is bottom up, okay, from components to the final assembly, and the second one from the assembly to the components, that is top down. The list of components used in a CAD assembly, that is known as the bill of materials, you all know by now. So, first let us look at a wireframe modeler. So, AutoCAD started off as a wireframe modeler. So, in a wireframe modeler there are two types of elements which are defined, the points or vertices and the lines or edges. So, using these points and by joining these points to create these edges, we can create the wireframe model of any object. So, what you have in the wireframe modeler is a list of vertices, a list of edges. Okay, these are the vertices, so the coordinates, and then the edges which connect the vertices. So, edge 1 connects V 1 and V 2. So, edge 1 here is connecting V 1 and V 2, these 2 points, and edge 2 is connecting V 2 and V 3, edge 3 is connecting V 3 and V 1, these 2, and so on and so forth. And then you can also have a face list. Face list is all these edges that comprise a face. So, F 1 is comprised of, if you see F 1, this face here is comprised of E 3, E 4, E 1 and E 2. So, E 1, E 2, E 3, E 4 comprise the face F 1. So, the vertex list, the edge list and the face list, if you can generate these, then you have created a wireframe modeler. So, that is what the wireframe modelers use, a list of vertices, list of edges and list of faces. Now, these wireframe modelers have some pros and cons. So, they are very simple to adapt from 2D software, they do not require a lot of memory, just edges, vertices and faces that you need to store, and then you need less processing power to represent them, and they cost less. But there is ambiguity. So, for instance, this is the wireframe model of an object. You have connected all the points to create these edges, but can you say whether it represents this or this or this? So, this wireframe model could represent either of these three. So, there is ambiguity in wireframe models. So, that is why the next generation of CAD software has used constructive solid geometry. So, constructive solid geometry allows flexibility in both how primitives are defined and combined. So, what you do here is you use operations such as union, difference, intersection, etc., to create your 3D objects. So, let us say you have rectangular parallelepiped and you have this cylinder, and then this rectangular box and this cylinder, if you join them using a union operation, you create a product like this. Okay. If you combine a cube with this sphere, then that is a union operation, but if you subtract this sphere from this cube, you get this sort of a shape, that is a difference. Whereas, if you intersect A and B, then you get the common area, which is this. So, constructive solid geometry uses union, difference and intersection to create your parts. So, if you go inside the CAD software, you can see you have these functionality present. union, difference and intersection. So, in SolidWorks they are typically referred to as join, cut, intersection, etc. So, sometimes these names do change with time. The key question is, does it matter in which order we do them? Okay, so, think about whether it matters if you do the union first and then the difference and the intersection, or if you do the difference first and then the union and then the difference, what product do you end up with? So, does it matter or does it not? Think about it, try it. So, go home and try it in a CAD package like SolidWorks or Inventor. So, you can see if you carry out the union of these two, you get this. If you carry out the difference, you get this, and if you carry out the intersection, you get this. Okay. So, here you see if you do A minus B and B minus A. So, if you do A minus B, you get this shape, and if you do B minus A, from B you subtract A, you get this thing. So, depending on what you are subtracting from what with the difference operation, you will get different parts. So, what we need for constructive solid geometry modeling is primitives. Okay. So, using primitives such as cuboids, cylinders, spheres and cones, you can create your product. Okay. So, here you can see there is a cylinder, there is a block, another block, and then there is a wedge. So, using such primitives, you can create your product. So, this is a camera and it has been created using these primitives and these operations. So, from A we subtract B to get this, then we do union with C to get this, then we do union with D to get this, okay, this cuboid, and then we do a union with E, this is E, to get this, then another union with this F to get this, another union with G to get this bit, and then we subtract H to get this final shape. So, that is what CSG does. Okay. Using these operations, you can get your final product. Everyone gets it? Yeah. The other representation that these CAD packages use is boundary representation. So, in the boundary representation, you use the surfaces or faces to define the solid. So, these surfaces or faces contain both linear and curved edges. So, you can see linear edges here and you can see curved edges here, these are curved, okay, and use these boundary representations to model your 3D objects. There are also surface modelers like CATIA. Again, they use points, lines to create actual surfaces. So, you can see this surface created in a surface modeler. Then there are hybrid modelers that combine CSG and BREP. Okay. So, this is a product that is made in CATIA. So, that uses CSG and BREP both. So, they use these union, difference and intersection operations, and they also use the boundaries of the parts to create your final definition. Whereas, if you had just solid modelers, there you just create the solid bodies, okay, where you can analyze them for volume, materials, etc. So, there are different types of modelers that exist. If you can get your hands on CATIA, I would strongly recommend it and see how it is different from other CAD packages. Okay, so let us summarize what we have learnt on the product life cycle and reverse engineering. So, the key phases of the product life cycle should be product, okay, development, introduction, growth, maturity and decline. Reverse engineering is a useful technique to analyze existing products and to use them to develop new products. Okay. So, reverse engineering helps you analyze what products exist in the market and also using them to develop new products. A crucial method in reverse engineering is tear down or disassembly. And 3D CAD tools, they enable efficient communication of product concepts and storage and use of product information through the product life cycle. Okay, thanks everyone for coming and see you all in the next class.